this in case he misses. So we started by talking specifically about, hey, when there's a structure, there are what are called reaction forces at all of the supports. If the reaction force is shown with a pin, we draw an X and a Y force. If it's shown with what we call rollers, these little wheels it looks like on the bottom, we only have a vertical reaction force. Now remember, if you think about this as a structure, I'm glad we're in this room today because it's easy to demonstrate actually. If I were thinking about, let's say this is the bridge right here, okay? If the bridge were fixed and supported vertically, the bridge was supported vertically like this, so my hands are holding it, there's nothing preventing it from sliding left or right. So I'm just holding it here. So it could easily slide left or right if there's any motion or any force applied. But the reaction force on the left, known as RBX, I can barely read it there, RBX, is preventing lateral motion. Yet the two supports are preventing vertical motion. So the RBY and the REY, or is that E? Yeah, REY, and then the RBX are supports. And what they're doing is they're keeping the bridge from moving. Okay, they're keeping the bridge from moving. Now, this is called a simply supported structure. When you have a pin joint on one side and a roller on the other. Simply supported is the phrase you'll hear in engineering classes. Now, what I want you guys to recognize is that even though we drew 1, 2, 3 forces, note that the diagram only has 2 reactions. The reason for that is that the applied forces are only vertical. In this scenario, there are only vertically applied forces. That's not always going to be the case. So think about wind, right? Wind would push this thing left to right more likely than up and down. So you could suddenly apply a force this way, and then that reaction force would come into play. Okay, so some of the scenarios we're going to do involve 3 reactions, some simplify down to 2. Now, where does the 500, 700 come from, though? That's the first question we have to ask ourselves. So we see the answer is there, and that's great. But how do we get that answer? So the first step in this general process, is to use equations of forces and moments. What did I use the word moment to replace from physics? I called them moments. I called them fixed end moments. What did they prevent? What does the moment prevent? It's a weird word. No. What is it? Good. What kind of motion specifically? They do prevent motion. Forces prevent lateral or vertical motion. Or motion this way. Those are forces. What do moments prevent? It's not translations. It would be. What would it be? Not reflections.
Up and down.
Not up and down. That's also translations. Translations are up and down, left to right. What am I doing? Rotations. Remember rotations? So underline the word moments here. You're going to hear that phrase a lot in engineering or in physics beyond Loyola. And moments refer to torques. Okay? So we're looking at the sum of the forces and the sum of the torques. And we use the phrase moments there. Now, if I were to look at my diagram, what I'll notice is that I don't have enough information to solve. How do I know that already? Look at my original diagram. If I sum the forces, you guys got to focus. Come on. If I sum the forces vertically, I could say that we've got REY plus RBY minus 400 minus 800 equals 0. And why do I equal 0 at the end? It's in the state of? It's got to be, right? The goal for all these problems is that the structure isn't moving. So it's in a state of equilibrium always. So what I'm doing again is positive because they're pointing up, like in physics. Negative because they're pointing down, and that equals 0. Now, can I solve for REY or RBY? At this point in time, can I do it? Why not? I'm seeing that now, or mathematically give me an answer. Can I physically solve an equation when there are multiple variables? No. What would I need? Software. Give me a lot of. You said software?
Software one, and then
Oh, solve for one of them. Okay, so what do I need? I need another equation. I need another equation to solve for one. I just said software. To solve for one of them, and then plug into this equation. So right now I'm stuck. I've got two variables, one equation. I cannot solve for these reactions. Well, what about the x direction? RBX, isn't that the only force acting? So again, this is sum of the forces in the y direction. That's the equation I get from that. Then I can sum the forces in the x direction. And that gives me RBX plus anything else? Are there any other horizontal forces in this diagram? I don't see any others, right? So RBX plus nothing equals 0. So what does RBX equal in this case? 0. That's what I looked. We can see in our answer, right, there's no RBX, right? This is RBY, this is REY. And let's figure out where these numbers come from. Let's figure out where these values come from. Now, first of all, why do you think there might be more force reacting on this side? Inspection, just by looking. Why might this force be greater reacting than this force reacting?
Because the force acting down on the right side is bigger.
The one that's stronger is more toward the right, so you're going to get more reaction here. Okay, that's going to cause that here. The one acting down here is closer, that's weaker, it'll be a weaker reaction. Now, is there a way to mathematically figure it out? Unfortunately, there's not. You can't just eyeball it, so we have to use another equation. I mean, look at this, right? 800 out of the total of 1200 is like 2/3, but this number isn't 2/3 of this, so it's not like you can use some proportion, you know what I mean? To say, oh, this one is that much bigger, so it's going to be that much bigger. It's not true. This is double this is not double this, right? So we can't just look at this and come up with the reactions. So we need a third equation, because the second equation I just wrote gave us no information. This was useless. Besides telling me that there's no horizontal reaction, which I could have figured that out by looking at the diagram simply, right? I could have looked and said, hey, this is the only horizontal force. There's nothing else acting this way, so this has to be 0. So that's useless. It doesn't help me. So sometimes the sum of the forces in the x and y are enough to help me, but not here. So instead, I need to do a sum of the torques, or sum of what we're calling the moments. So let's jot that down as sum of the moments. Now, for summing moments together, you have to pick a point to rotate about. Remember how torque worked? Torque was a force acting at a distance from the rotating axis. A force acting at a distance from the rotating axis. A force acting at a distance from the rotating axis. So, where might I choose my point of rotation for this bridge? What might be a useful decision to choose for the point of rotation? And it might not be obvious because we haven't done this in physics. It's a little bit, it's an extension of torque. But I'll give you suggestions or choices. Let's choose B, C, or E. Out of B, C, or E, which of these should I sum the torques about? And why? Out of B, C, or E. Let me give you.
What do you mean by summing?
Okay. So what we're going to do is we're going to look at the sum of the moments, like we sum the forces together, add them up. Mm-hmm. So we're going to add the torques from all of these forces acting. So for example, Alex, this force is applied here, this is applied here, and applied here. So there's 4 forces right now. So each of these forces creates torque. So if I'm rotating, take a look where I'm pointing. If I'm rotating about this location here, then this one would cause clockwise rotation. This would cause clockwise rotation. This would cause counterclockwise. Remember we did this last year? But this one, RBY, how far is RBY from point B? It's not a trick question. How far is RBY from point B? How far? None, no displacement, 0, right? So remember from last year, from torque, when I did this, when I push the door here, it's very easy to open with torque, right? As I get closer, it's harder, isn't it? Remember we said this? But when I was on the rotating axis, remember I said this is like impossible? And if I'm literally here, I can't do anything, right? Close his arm, he hasn't doing anything. So if you apply a force at the point of rotation, it doesn't generate any sort of torque. So if we sum together the moments, the torques, at either B or E, it will allow us to ignore either of those forces depending upon which one we choose. So let's choose for now that we'll sum the moments at point B. Okay, let's choose point B here. So put a subscript. Put a subscript. Oops. Now, if I'm summing together the moments at point B, I have to think how far is this force acting perpendicularly from point B? How far is this force acting? Remember, this is my D value, or R. Remember, FR sine theta? So the theta value, if you take this force and extend it down, theta is going to be 90 degrees, so you don't have to worry. This theta value between the lever arm and the force is 90 degrees. Taking this force, extend it down. There's the distance again, and this is again 90 degrees. So we have three forces that are causing the bridge to rotate about this point. This force does nothing because its distance from B is 0. And remember, distance in the formula comes into play a role. So before we use these numbers, we're going to use these values here. So let's write our equations out. So we could have the torque provided by REY, and I'm going to see that as REY times the distance from the rotating axis. How far is REY from point B? From the diagram, how far is it from point B? REY. The one on the far right. How far is that?
4 meters.
4 meters away. So remember my equation. If I'm forgetting right now, some of you have a little confused look, I'll put it at the top. Okay? Remember, that's the equation for torque. R times F sine theta. Our thetas are going to be pretty much 90 degrees for all of these, unless a force is applied at an angle. And then we'll use sine theta there. But ours are going to be mainly 90 degrees. I could also just put a little symbol here. Take a look at the symbol I'm going to put next to R. At the top, I call that R perpendicular. R perpendicular. Because, ready, watch what I'm going to do. If I were to really look at this force right here, and I think of this force applied right there, and this is the rotating axis, then technically this is R. And then the angle is some bigger angle, right? But I'd rather just drop this down to here and use 90 degrees and just figure out what this value is. Now, simply because of the fact that I know there's symmetry in this, and it's coming straight down from the vertex, and these are what kind of triangles? What kind of triangles you're picking up on these are? Equilateral triangles. Now, the reason I know that, the only reason, and this is 60, sure, but how do I know these are 60? Well, if this is 60 here, and these are all the same length, 2 meter spans, these have to be 60, 60, 60 to make 180, right? So I know these will be 60. If these are 60, then the remaining one is also 60. So it's a set of equilateral triangles. So what I'm going to do is I'm going to take that force of 400 newtons, take a look at the top diagram, please, and I'm going to extend it all the way to there. And the same thing with the 800 newtons. I'm going to extend it all the way down. And now, this in blue, is my R value for the first force. That's the R value, and now it's at 90 degrees, and there's the angle, or there's the value of the force of 400. It just simplifies matters for me to do it this way. So my REY is a distance of 4 meters away. What else can you tell me? And REY pushes this object which way? Does this REY cause it to go clockwise or counterclockwise if this is fixed? Yeah, think about it, right? Here's the object. Marker is the bridge, right? Remember we talked about some physics. Fix at B. Apply a force at E, and watch what happens. It rotates this way, right? Clockwise is always positive. Counterclockwise, which we're talking about here, is always positive. Now, the other two forces acting down on the top of the bridge are going to cause what kind of rotation? The two forces acting down cause what kind of rotation? Clockwise, right? It's going to continue this way. So the 400 and the 800 Newton forces are going to cause negative torques or negative moments. So we'll put minus next. The force is 400, and it's acting at a distance of 1 meter from point B. And then finally, 800 newtons is acting at a distance of 3 meters from point B. And that equals 0. Why did I not include RBX again, or RBY? Why didn't I include RBX and RBY in this sum of the moments? Why not? Why not?
There's zero displacement. So
Good. Zero distance or displacement. So look, I would do RBY times 0. RBX times 0, right? You see what I'm getting at there? So the distance away from the rotating axis is 0. So it's going to always create a 0 torque from those two parts. So take a look at the moment equation now. What does this allow you to do?
Solve for REY.
Yeah, and then once you have REY, what did you say we should do with REY, Alex, once we have it?
plug into the on the top, the solve for RB.
Okay? So the goal in these processes is to start by looking at the bridge as an overall structure, do the sum of the forces in the X, sum of the forces in the Y, and then you have to do the sum of the moments about whatever point you choose. But choose wisely. Choose wisely. If you have two forces acting at a location, do the sum of the moments about that thing, about that point. Because it removes those two forces as role players, as effectors in the sum of the torques. Okay, so let's go ahead and solve for REY. So we got 4REY. I'm going to add those other things to the side. 800 times 3 is 2400, plus 400 is 2800. So REY is going to be 700. And that's what we expected because our diagram had the answers on it, right? We saw this earlier. So we expected to get 700. Now, again, as Alex mentioned, if that's 700, we take that value and plug it back in up here for REY. 700 plus what number will give me 1200. If I move the 400 and 800 over, that number is 500. So we take REY, plug it back into the forces, and get RBY. The process for this is the same for every single bridge. You know what gets tough, honestly? Here's what gets tough. Trig. Some trig is involved at times, some sine and cosine can be involved, and a little bit of geometry stuff. But you're always going to do sum of the force in the X, sum of the force in the Y, sum of the torques or moments about some point you choose wisely. Okay, it's never going to change. That's really step one for this process. There are two steps. That's step one. Let me write down what RBY is because we're going to really solve for it. So once we plug in for REY in this top equation, we'll be able to solve for RBY, and that will equal 500 newtons. Now, that's all great. Right? That's great. We've got a value of that. We've got an idea of where we're headed. But now we have to look at each individual pin, aka node, joint, where the two members meet, or where the four members meet. We need to analyze all of these different nodes. And we're going to analyze all of them in a 3-body diagram. And we're not going to have to worry about torques for these. It's just going to be some of the forces in the X and Y. But a lot of trig. Before I go on to that, lunches today or not today? Who? Is it just you?
5 minutes.
What do you got?
5 minutes.
5 minutes? So how about during the break, or do you want to leave early? What's better? There's probably actually more traffic, right, if you go after?
Will you go to break?
in 5 minutes. But I'm saying, like, do you want to go during the break or go right now and just get it done? I'm going to continue, but I can wait till you get back. I don't mind. I'd rather you get the lunch now because it's quicker because there's no one online, right? Because if you go at the beginning of next period, you're going to wait online.
Okay.
The 7 members in our sample need to be analyzed and determine how much force is coming from them. So the way to do it is what you're seeing here at the bottom, is to draw a free body diagram of each of these nodes. So, notice several things here. At each node, we'll see that we have many other forces. So for example, at node A, it doesn't make any sense to analyze this. Why? Why doesn't it make sense to analyze node A? What did we just say a little while ago? For every unknown, you need at least one equation. How many unknowns are here? And what did I say? How many force equations do we have only? Force only. You only have 2, x and y. Moments are not used. Why are moments used? Well, how far from the node is this force acting? 0. How far away is this acting? 0. So we cannot use the sum of torques or moments for the nodal analysis part, right? So as a result, it doesn't benefit me or you or anyone doing this to look at node A. But take a look, ready? Take a look. This is what I like to see. If we look at node V, how many unknowns are there? For node B, how many unknowns are there? 2. FBC and FAB. But look, if I get FAB, don't I also have FAB over here? Because what connects node A and B is member AB. So the force that's acting on node B also acts on node A. And let's look at our diagram to see where that is. And there it is. There's the member at the top. So this force coming from node A and from node B is because of this member right here. So if I can find the force in AB on node B, I can use that for node A. Is that clear what I'm saying? For these forces are equal and opposite. Equal and opposite. So, what I want you to recognize first is looking at the orientation and the angles. The angles that these forces act affect the overall results of these forces. So the 60-degree angles are very important. So notice on my free body diagrams, what do I include? Or I don't have booked it here, but what would you include would be all of your geometric constraints. Why might I not need to put an angle here? It must be what value? Angle between these two. What value must it be? 60. Because this is 60, this is 30. What does this whole thing make up? Angle, right angle. So it's not shown in the diagram, but this is 60 degrees right here. You probably do want to label that. This is 90. You don't have to label 90, but put a right angle maybe. 60, 90, right? So you have our labels. So let's together, let's analyze node B. Now, to analyze this node, I need to look at the sum of the forces. How many forces are acting in the x direction? Good. Now, you correct yourself. It's not just one. FBC is only the x, but FAB, FBC is only the x, but FAB is the x and the y. Think back to vectors from last year, right? Vectors. So as a result, I have to split FAB into its components. So I'm going to do it the same way I did last year in physics. I'm going to start by drawing a vertical component and a horizontal component of FAB. This is FAB times the sine of 60. This is FAB times the cosine of 60. We then have FBC also acting. And then we also have 500 newtons as our reaction force pushing up. So what I've done, here is I've taken our diagram, our free body diagram from physics last year, and I've drawn the components of the force that acts at an angle in the X and the Y specifically. Because this is only in the Y, this is only in the Y now. So that allows me to say I can find FAB if I have only two forces in the Y. But I've got two in the X, so I can't use the X right away. So let's look at the sum of the forces in the Y direction. We always know it equals 0. Why does it always equal 0? One word. Equilibrium. So in the vertical direction, what forces are acting up or down, respectively? In the vertical direction, what's acting up, what's acting down? What's happening here? What's happening? 500 is acting which way? Up. So it's positive. What else is acting up? FAB. Keep going. Yeah, sine 60, not just 60. FAB sine 60 is at. So these two forces right here and right here are both pushing up. So I say 500 plus FAB sine 60 equals 0. Remember, the way that this works is any force is acting up, become positive. Anything down, negative. Anything right, positive. Anything left, negative. Now, yes, I understand. I see what you're looking right away. Some of you gave me a look like, that's weird. Two acting up, that's not possible. How could that be equilibrium, right? It doesn't make sense. If one acts up, the other acts back down, doesn't it? So what kind of an answer is FAB going to be? Negative. Because FAB really, although we drew it acting up, FAB is indeed negative as an answer. So let's go ahead and solve for FAB. Let's move the 500 over. By subtracting it, and let's divide by the sine of 60. What do we get for FAB? Negative 577.4. I will take Will's advice unless somebody tells me otherwise. Now, is that correct?
The next would it be on, would your calculator be on the
Because your angles are measured in? When the angles are measured in radians. So yeah, FAB is negative 577.4. There's a general rule, and it's a little bit further down in your diagram. You can see it actually. It says, a positive force indicates that the associated two-force member is in tension. And a negative force indicates that it's in compression. You know these phrases because you did that applet that day when I was out. Compression is physically squeezing. Tension is pulling. So since this answer was negative, it indicates that FAB is in compression. FAB is in compression. Now, here's the thing. FAB also affects my answer for FBC. How so? How does FAB affect FAC? FBC, sorry. Look at my diagrams. How does FAB affect FBC? Or how will they be used together? How will I find FBC is what I'm asking. How will I find FBC?
Don't you have to like plug in? You have to plug in something from there.
You definitely have to plug in something from there. I agree, but I need more than that.
Um,
How about?
Isn't FBC and FAB going to the same side? Doesn't FAB affect FBC?
It does, but I know what you're saying, but I need you to give me more with math and like equations. How are we going to use FBC and FAB? How are we going to find FBC is my question.
you have to add it to FBC.
So what are we doing then?
Adding.
More general physics terms.
We're adding the forces.
In the?
X.
Thank you. So we need to sum the forces in the X and recognize that, look, FBC and FAB are both acting in the X direction. They're both acting in the X direction. So as a result, we need to go ahead and figure out what that'll become. Try it on your own. Sum of the force in the X. See what you get for FBC. Right? FBC in this one. God bless you. What do we get for FBC? Chris, what do you got?
288.7.
Can I check with others?
Yeah.
Christian, yeah, same thing? Well, okay. I'll agree if 3 say yes on that. I'm trying to look ahead to see if I want to include a little bit more from this problem or go on to the actual problem we're going to do. Okay. Let's go through the other nodes. So let's see if we can get all of these values. So at this point in time, we've got 2 members. How many members do we need though? Or how many members do we have in this bridge? Looks like 7, right? We had 7 members. So what's nice is sometimes and most times, one node will give you 2 members. You know what I'm saying? So how many nodes are we going to have to really look at? 3.5, I guess. Right, analyzing 3 nodes will give us about 6 members. We have 7. So if I look at these choices now, what are you going to choose? Now let's do this. Let's cross out what we know. How about that? Okay, let's cross out what we know. So tell me, what was again FBC? What'd you say it was again, Chris?
388.7.
And that's FBC, so that's also here. Anywhere else? No. And then FAB. FAB, what did that turn out to be again? What was it?
-577.4.
And the negative is important. Remember to put it there, please. The negative is important. Okay? So that's what we know now. Choices. My question first. Which two nodes can we not choose? Which two nodes can we not choose to analyze? Still. There are two of them that still we couldn't work with. Definitely the one in the middle, because how many unknowns, Katie? Yeah? And D. Good. 1, 2, 3, right? So nodes C and D are still useless to us because we don't know enough information. But we can now go back to node A and take a look at it. We could also go to node E at any point in time and take a look at it. Does that make sense what I'm getting at right now? Okay. So I'm going to go to node A next. I'm going to go to node A. I'm going to draw it down here. Watch what I'm going to do. This negative 577, I'm going to leave it the way it's drawn. I know negative means it's just in compression. So really it's the opposite direction that force is acting on the pin. But what I want you to recognize is just draw it the way it is and label it the negative and you won't have any problems. We know that this angle is 30. We know that this force is also at an angle of 30. We know that this force is acting horizontally and that there's a weight acting on the bridge with 400 newtons. Now, if I look at this diagram and I ask myself, all right, let's go to the x and the y direction. What's the one thing I need to change though? Or what's the one thing I need to look at differently? Think about when we did the x and y direction for the last problem. There's one thing that's wrong with my diagram. Not wrong with, but I should kind of draw differently or denote differently on the diagram. 400. If I use cosine and sine for x and y, what do I have to remember? If I use cosine and sine for x and y, what do I have to remember? When you are finding the use inverse, but I'm saying when I find the x component or the y component of a force, what do I have to remember about the angle? About the angle. You had an idea before I said that? No?
Like, make it negative, something like
Negative. From physics last year. If I'm going to kick a football, right, and I punt it, and I punt at an angle of 25 degrees above the horizontal, I always use 25 degrees as my answer. I don't ever use 65.
Is it because like the way the projectile thing is? Like if the angle is too big, it's mostly straight.
Yeah, that's true, but that's not what I'm getting at.
Isn't that like, it's angle from the y-axis instead of the x-axis?
Yeah. In this diagram, the angles are measured from the y-axis. And remember what we've talked about? Sine and cosine, that whole concept of making cosine x and sine y is only true when your angles are with respect to the x-axis. So the angles that we're going to use in this figure are not the 30 and 30 at all. They're the 60 here and the 60 here. Is that clear what I'm saying? Okay, so we have to make sure we note that right now. So we remember that when we get to the bridge analysis. We're going to do a couple of these. This is one of those topics where I will probably give you like an actual quiz. I rarely give you guys quizzes. And probably like a homework assignment or two on a couple of nodal analysis of bridges. Now, I want you to remember though that angles have to be with respect to the horizontal. So when I look at this now, and I want to sum the forces, I can sum in the x or the y, it doesn't matter. I'm going to start in the y though. Why am I starting in the y in this case? How come I'm summing the forces together in the y direction to analyze this node, and not the x? There's what? Okay, I like that more, or better information in the y. What does come out to mean by that? What's the problem with the x direction? How many unknowns am I going to have in the x direction? FAD for sure, right? That's only in the x, and isn't this in the x and the y? So this has a component in the x and a component in the y. So I really can't be focused on the x direction because I have FAD and FAC cosine 60. So I can't solve for two variables with one equation. So let's start in the y direction instead, because only FAC acts in the y direction. I mean, 577.4 does, partially, and 400 does completely, right? So I have to consider that fact. So starting in the y direction, I've got the following. I've got negative 400 to start, because that's acting down. I know that FAC is also acting down. I want the y component, so I do sine of the angle, which is 60. And then I know that the 577.4 was drawn down. So watch what this becomes, please. It becomes minus because it's drawn down, but it's a negative, isn't it? So that's what I meant earlier. That's what it becomes. And this is sine 60 also. And that equals 0. Why is the 577.4 times sine 60? Because it's acting left and down. So the down component is the sine part, right? The sine. So when we look at this setup, we can see now, what can we solve for? What can we solve for here?
FAC.
Solve for FAC. Then I want you to write the equation of motion for the x direction. Sum the force in the x. You'll have two unknowns. One of them will be FAC. Plug that in and get the other unknown, which will be FAD. So finish the y direction, get this value, go to the x direction, and help to find FAD. Check with the person next to you, please, if you want. Check that you got the same value for FAC, so you don't go on with the wrong answer. You follow me? So before you move on to the next part with the x direction, look at FAC's answer. Nodal analysis. Their structures. So looking at truss structures and how the members, the two force members, each are connected to a load and identify the strength. The force acting each one. See if we see the strength. So if it'll snap or compress, compress or snap. Yeah, basics of civil engineering when we started. Yeah, so when we first started, I was at MIT in the beginning, first we learned the model every time, It's the intro stuff. There's no way to tell. We talked about suspension, like a model one last week with like straws and dental floss, and we talked about the concept that the weight on the bridge gets displaced into the cables and then eventually into those whatever they call abutments at the end. When we can do the math and suspension is very different. Truss structure because everything's linear. It's all transmission. So you can go on straight. But other bridges you start to use calculus and different things. So this is just give me a nod when it goes. Okay. So I'm going to write this down for that. FAC?
115.52.
Christian? Alex, Rodrigo, Katie, Clemence? Clemence, nah, she's like, nah, it's not happening. So what was it?
115.52.
So if I were solving this, just for those that maybe didn't get it right, I would add the 400 over to the left side first, right? And then I would take this whole quantity, and it's a double negative, which makes that a positive, so I would then subtract it over. And that would equal negative FAC sine 60. I would then divide by negative sine 60 to get FAC by itself. Say it one more time, Will.
115.52.
Thank you. So if you're having trouble with this, or if it's just entering in the calculator, check that you're in degree mode, obviously. But just think about the math, right? Negative, move it over as a positive. Double negative makes that a positive, so move that over as a negative. And then divide by the coefficient, which is negative 1. And then sine 60 is also the coefficient. So divide by negative 1 sine 60. Go to the forces in the x direction. And think about what your governing equation would be. So I'll give you a little hint with the governing if you haven't written it yet. And there it is. There's the governing equation. It's just sum of the force equals 0, right? Then we plug into that. So in the x direction, I've got FAD pulling right. I've got FAC pulling right at an angle of 60. I've got negative, and this is negative negative again, 577.4, that's pulling left at an angle of 60. And that equals 0. Plug in for FAC from your last answer and get FAD. Why didn't I include 400 in x direction? Why did I include the 400 force? Good. The 400 acts down on the bridge. It acts down. So it doesn't affect the horizontal motion in the center. Technically, that is a closed figure if we make a line on the side. And that's not there. It's not there. So that's a closed figure. Now, you want to extrude this piece right here. Oh, okay, so you want to say. Any reason you didn't use the symmetry tool? Imagine you know it's an injection of just tangent features and so
What do you get? About negative 6
That's what I got.
now you want to extrude both, right? At the same time. Hold down control. Zoom in on that where they cross. Try to just extrude all of this piece first. Try. I want to see like just one of those straight ones, not out. And those lines just
I got none.
Okay. Oh, yeah. There you go.
So there's this, and there's this one. Unfortunately, it's top line. Possible. I didn't see it turn green for one reason. Green usually is moving in, right? Obviously, I think you had it. This is not what we have here. It is. It's like it's
Okay,
called
I was
post
just
snap or
unsure.
something like that.
Just, no, okay, so,
It's probably in your settings somewhere. So I went to file and then choose options.
I'm shook.
I'm pretty sure it's in your
I'm so
somewhere.
sure.
You can just go, this is a lot. It's
No.
definitely in there somewhere. It's in the sketch.
Is that possible? Yes.
Snap.
That's possible. This is
So maybe try to redraw those, let me go over this one now and come back to it.
This is
Did we get a
like,
FAD?
Wait, shouldn't you be doing some cosine?
but.
Sorry, those should be cosines, guys. Yeah, thank you.
That's why I was confused.
Sorry, guys. Sorry. Why don't you guys correct me? I can make mistakes too. I'm sorry. It's definitely cosines. Yeah, it's the X direction. So you've been trying with sine the whole time and it wasn't working out well? Never trust me again. Never. Yeah. It's the first mistake you made was trusting me in the beginning. Come on.
I have 346.46.
You had 3.
346.46.
What'd you do?
346.
Yeah, it's back. It's not.
I want you to do it though before you just say you got X to them say yes. I talk about them physics a lot, guys. I do. Because this year's junior class is good. A lot of them don't like to do the work in class, and they just like one person like, oh yeah, the answer's this, and they'll all nod their head like it's right. And yet on the test, they can't use the calculator; it's just in their practice. So we got to practice. Is what I'm saying. You know, practice going through the process. It makes you a lot better at it. I got Chris and Will's answer. Just want to make sure everybody agrees with that.
Shouldn't it be negative?
Is that what you get? Negative? Yeah, it definitely should be negative based on the math I'm looking at. Am I correct, guys? Negative for sure, right? Because this is negative, as long as the math is right. This is again, right? This is two negatives, makes that positive. So I move that over by subtracting it, and that's this right here. And this is positive already, so I move this whole thing over by subtracting it, that's this right here. I had FAC from the last part, we plug that number in right here, and then negative this number minus this number should yield a negative answer.
Wait, why is AC negative?
Because I subtracted it over from one part of the equation, it was on this side, and I moved it over to this side of the equation. So I subtracted this entire thing over. It's not that AC is negative, it's that the quantity here, look, like that, Alex, that's how it should be written, I guess, okay? The whole quantity is negative because it was moved over.
Do you have an action calculator?
You don't have an action. Oh, you're using the iPad for this? Yeah, I would not use an iPad for anytime you have trig, use a calculator, regular. Yeah, the iPad doesn't help much. Yes, Chris. Yeah. I want to finish the last node. That's 4 forces down. So let's go back to our diagram. Help me out. Please remind me. So FAC 115.5. Let's label that. And then FAC should show up somewhere else. So here it is.
Is it FED?
And then FAD we got. FAD, we just said negative 346.5. So again, notice what's happening here. As we acquire more of the answers, the problem just gets easier. It just gets easier. Now, we have chosen node A and B to analyze. So we're obviously not going to choose A or B, right? Because we know everything here and we know everything here. Does it matter which of these three I choose next? What do you think? Does it matter which of these three I choose next?
No, because they both have two.
Okay, no, because they all have two unknowns, but one is better than the others. Or two choices is better than one of them. Which choice is not the one you want to start with? Last one will work. You can do that one. Why not?
Because one, two.
You have two. It's not about 2 or 1. Remember, we said all of them can be solved. But this one and this one would be a lot easier to solve than this one would. Why is this one going to be tough to solve? Both of these forces are at
X and Y.
they both have x and y components.
And then but there's no force going to the right.
So what does that mean if they both have x and y components? Look, FED has FED cosine theta, FED sine theta. FCD has FCD sine theta, FCD cosine theta. So if I do the x and y direction for this one, I'm going to have both equations with 2 unknown variables. It'll be a system you have to solve. So if you choose node D to solve, FCD and FED are going to show up in both the x and y directions. Therefore, you'd have to solve 2 equations with 2 unknowns, which is a system. There's no need to solve a system when you can use these instead. Look at this one. FCE is in the x only. So that makes it easy. We can solve for the y instead first. So let's choose node, I'll choose node E actually. Let's choose node E on the far right. Probably going to run out at 11:46? 37? 37? Oh, it's 12:37. That's fine. All right, we got 5 minutes. We'll get node E. So let's take a look at node E. Only 2 unknowns, so we can definitely solve. FED acting at 60, FCE acting to the right. So there's my free body diagram. With that free body diagram, I could write my equations in the y direction. I've got 700 acting up. I've got FED times the sine of its angle. That equals 0. Why is FCE not included here? It's only acting the x. So in the x direction, I've got negative FCE minus FED cosine 60 degrees equals 0. So if I started in the x direction here, it's apparent that you cannot solve because there's two unknowns. This is what would happen at node D. As Katie mentioned, at node D, this would happen in both the x and the y direction. You'd have two unknowns in each equation. You'd have to use a system using substitution or elimination to solve. So I chose node E for that reason and not node D. Okay? Node E. Go ahead and solve for FED, and then go ahead and plug that in and find FCE. I mean FED first, obviously. FED first. Did it work? Probably is a solution that you could probably use. It might take more time to figure it out than it would to actually design it somehow differently. Not differently, but like using some sort of symmetry, you know? For example, can I make a suggestion? Is the wheel going to be extruded out the same exact dimension as this is extruded out? So technically, instead of connecting these lines, a lot easier. You can make these rectangles a little further to here. Extrude or extrude that, it'll work. You know what I'm saying? Because of the relation. No, only if you choose it. You could extrude over an object and it just melts to it and merges with it. So what I'm saying is possibly consider extruding only the outside first. Whatever dimension it is, it looks like everything's gone. Yeah, that's great. Now, it's not gone, obviously. It's just the sketches. So now we can do a second sketch, right? I think you literally just lose, and maybe it's just not just the average, but you make a bunch of rectangles that somehow get in here and end up like
Must be a reason.
this is the extruder also. Consider doing that, like, I'm not going to extrude the outer and inner faces. Guys, have a good day. I know it took a little longer than we expected. Please tell Chris that if I'm going to put this online, you should look at it before next class. We have a double next or single? Single next? We'll finish this, then we'll start the project in a double. Okay, guys, have a good day.
We're gonna have to do to resolve this, we have to.
Yeah. So this is where we left off. So I said to you guys, figure out what FED is. And then once you have FED, plug that in right here, and then solve for FCE. So what did FED turn out to be yesterday? Who had a number yesterday at this point? What was it? 700 divided by sine 60, right? Or negative 700, because we're going to move the 700 over and then divide by sine 60. I don't have a calculator, so I'm relying on you guys to calculate this stuff, right? And really we should all be practicing stuff like this. We should be able to use our own calculators to do this. So again, move 700 over, and you'll be left with this. And then divide by 700, divide by sine 60 on both sides. And let's get at least 2 people to confirm the answer, because we want to make sure we're in the right mode and then we're doing it properly.
So it just means negative 700 over sine 60?
Correct.
I
Yep.
got negative 808.
808.2?
Yeah.
0.3 if I rounded? Okay.
Yeah.
Agreed? Okay. Now, that's the force in member ED. You should actually calculate it, not just say yes, please, right? We said that yesterday. So FED, remember, is this right here. That's what we're getting from this result. Well, FED starts at node E and extends to node D. So it's the same force, and let's show why that is. FED is really doing what? It's the force connecting this to this. So although we're looking at node E right now, and we're getting FED pulling out this way, well, FED also comes out this way. So in that diagram, for our nodes now, again, you said 808.3?
Mm-hmm.
Okay. So we can cross this off, 808.3, which makes this also 808.3. Now, is it negative?
Yeah.
Yeah. And remember from yesterday, we also concluded negative means compression. It means the member is being pressed. Positive means it's in tension. Okay? So what does this allow us to do? First, we can continue to find FCE, which we still have to do for member E, for node E in a minute. We'll go back to that. But also, we can look, God bless you, over here and see that, hey, now we've got this force. We've got this force. We've got this force. We could also find FCD, which is the one that's missing still from node D. So let's go back, though, to node E, where we just were. Let's go ahead and find, from the x direction now, what FCE is. So remember, it was negative FCE because FCE was pulling left. It was negative FED cosine 60 because that's pulling up and left. So it's all about pulling left here. That makes those both negative. So I've got negative. Yeah, what do you got? Sorry.
So it'll just be at 808.3 over this 60?
Uh,
Over or no?
Well, we're going to move it over. Yeah, so we're going to have a double negative there. Correct. Yep. So we're going to have a negative with another negative because we're carrying it down from the one above. And that's going to be cos 60 right there. And that equals 0. So again, I'm taking this answer and plugging it in right there. And when we do that, we'll have, a double negative moved over, which will make it negative on the right. And then dividing by another negative will make it positive in the end. So what do we get when we do 808.3 cos 60 and move it on over? Going to be less than 808.3. We know that. Is cos
4.5?
Yeah. Cosine 60 is 1/2, so it should have been half of that value. Very good. 404.15. And that's going to be a positive answer for that value. Again, because look at the math going on here. We've got a negative, which makes this a positive. So we would subtract it over to this side, and then we would divide by the -1 that's in front of that value. Okay, so I'm kind of doing a lot of the algebra without showing all the work. So keep in mind where that answer comes from. So 404.15 is FCE. Let's go back to the diagram. We'll take a look. It's over here also. FCE is also coming from node C. 404.15. So looking at my overall nodal diagram,
Find FCD.
it looks like, we're just missing FCD at this point. We found all of our other single forces, which were really paired up with another node, so we eliminated a lot of the node spots we didn't have to worry about. So it looks like we've analyzed 3 nodes so far, and that gave us 6 forces, and that makes sense, right? every node should give us 2 forces answers. So we have 6 answers by analyzing 3 nodes. Well, there are 7 forces because there were 7 members. So we have to work on 1 more node. So what node would you recommend at this point? We've already analyzed A, B, and E. We've done A, B, and E. Would you next choose C or would you choose D?
C, D,
Which one?
D.
Why?
Well, because it's C is kind of has everything in it, which I don't know if it would be like either helpful or confusing, but D is kind of more isolated to that one part of it.
Okay. But they both have 4 forces still, right? If you look at them. Anybody else? Impact? Input? What do you think?
D has 1 horizontal, 1 force is just on the Y, 1 is just on the X, and only has 2 that are, but so does C though.
And so in the end, yeah, in both cases, I wanted to point that out. Look, this is horizontal, this is horizontal, this is vertical, this is horizontal. But this force and this force are at angles. This force and this force are at angles. So in the end, it's 6 and 1/2. It doesn't matter which one we choose, right? So I'm going to choose node D. Okay, just because both Katie and Rodrigo chose that and it really didn't matter. So I'm going to choose this node to analyze. So I need to copy these values down here. So 346.5. I'm going to do it over here actually because we have room. Now be careful, remember, and this, Chris, this was something that was a little tricky. The 346 was negative. Now, this arrow is drawn left still. Again, what am I referring to? I'm referring to this right here. Oops. Referring to this over here on the right. That 346 turned out to be a negative answer when we got that earlier. So although it says negative 346 right there, this arrow is still drawn left. So when we do sum of the forces, this is going to be left in the x direction, but it's going to be a negative. So it'll be a double negative there. Okay, it'll be a double negative. Then we've got FCD acting down left and 808.3 negative. And we want to remember that this angle is 60 degrees. And this angle over here is 60 degrees as well. The key for these problems is to remember again that your angles have to be measured with respect to the x-axis. So I'm not going to use like the 30-degree angle that may have been given in the diagram or a 60-degree angle with the vertical. I'm always going to use the angle with respect to the horizontal. So there's my free body diagram on the top right. And now I need to start looking at my equations of motion. And remember, I don't look at torque for these. I don't look at torque. I look at the sum of the forces. So I start with the sum of the forces in the x direction. Now, take a look at FCD. It's the only unknown. Everybody sees that? So do I need 2 equations then? So I could pick either x or y. If FCD were only in the x, I would do sum of the force in the x. If FCD were only in the y, I would do sum of the forces in the y. But it's in both directions, right? And it doesn't choose one. It doesn't make it easier one way or the other. So I'm going to choose sum of the force in the x. And we always set it equal to 0 because we're assuming the bridge isn't moving. Equilibrium. And that is an obvious assumption, right? We don't want the bridge to move. Bridges vibrate, but those are small oscillations that are negligible. But if a bridge physically were to move, it would cause catastrophic failure, unless it was a drawbridge, obviously. So sum of the forces in the x. We've got negative, ready for this? Negative 346.5. And that's a little confusing, but look at the free body diagram. The arrow is drawn left, which is where this negative sign comes from. And then because the answer we got was negative, it meant it was in compression, we have to carry that negative over every time. Because really what it means is that this force is really pushing to the right. When this was a negative and it was drawn left, it means that we kind of drew the arrow wrong. It doesn't matter, but this force is really be pushing to the right, which is negative, making it positive. Then I've got negative 808.3, but that's at an angle. So now I'm looking at this force over here, but it's drawn at an angle, so only part of it is pulling to the right. And that's the cosine 60 part of it. So this is going to be, and stay with me here, it's going to be plus, because it's pulling to the right, but then it's going to be negative, because it's a negative value, 808.3, times the cosine of 60 degrees. That's going to be its x component that's pulling to the right. Again, I know it says negative, so there's a negative in there, but it's positive because it's pulling right. And then finally, FCD is pulling to the left, right? FCD is pulling to the left. So when we look at FCD here, we're going to put a minus for that, and that'll be minus FCD, and again, cosine 60 for that one, because the angle on both sides is 60 degrees on both sides. And the sum of all those forces equals 0. And again, why don't I include the 800? Why don't I include the 800? Only acting in the y direction. Only in the y direction. So let's go ahead and get FCD, please. Let's solve for FCD. Now, if I were to do this algebraically, I could do a lot of manipulation and move stuff over. So I see 346.5 as a positive, so I'm going to move it over to the negative side, the right side as a negative. Right, a double negative makes that positive. Move it over as a negative. Then I'm going to take the 808.3 cosine 60, move that over as a positive because it's currently negative. And then that's going to leave me with negative FCD cos 60 on the left-hand side. So I'm just moving all my constants over to the right-hand side. I then divide by negative cosine 60 to get FCD by itself. This is kind of like physics last year where I would have you solve algebraically and then get the answer at the end. We have numbers, but I'm still having you arrange it, or I'm still going through this algebraically for now. Okay, so let's compute this. You got it? Yeah?
Negative 1,154.8.
Can I get a verification from one person just to make sure we're working with the right answer? Let's see logically, Katie, if it makes sense. 800 cosine 60 is 1/2. That's going to be, wait, cos 60 is 1/2. Are you sure? I think I'm getting something different.
I got negative 115.
I think you're off by a factor of 10, Katie. Negative 115 is what he got. Check it one more time. Because just doing quick mental math, it seems a little bit high for a value for this number. Negative 115.3.
Yeah.
Can somebody check if they got that number, please? Making sure again that our mode is set to degree mode.
Yeah, I got negative 115.3.
What'd you get? Okay. On the phones, you got to be careful. Two things. The phones on calculators, to be in degree mode, you actually have to see the word rad on there somewhere. If it says degree right now, actually, like, can I see yours, Chris? Do you mind? Oh, that works then if you're using that one. Are you using the phone's calculator, though? The phone calculator's a little bit funky, so be careful there. Like, you have to type in the angle first, then press cosine on the phone calculators. Whereas on a real calculator, press cosine of 60. So that might be a problem with yours, so just keep that in mind.
I got the same thing, but Will just did it in parts, and he got what Alex got, so maybe I should do it smaller.
So, you know what you probably did, Katie? Look, did you forget your parentheses around this whole thing?
Oh, yeah.
Yeah, because you're taking an entire thing, summing it, and then dividing. Your calculator instead will do this. It'll take this, and it'll divide it by this, because PEMDAS says to do division first. And then it'll take that answer and add this to it.
Okay.
That makes sense why the answer is different. Yep. All right, so anyway, we get an answer of negative 115.3. So we have an answer that tells us that this last member is in compression. So a lot of the time when you do a nodal analysis, the end goal is to just label each member with compression or tension in each member. So we can go back to the original if we wanted to do that and just label with plus or minuses. So FCD was negative. So on my diagram here, that's going to make this compression right here. So I'm labeling the top diagram up there. I don't know what my other numbers were. I gotta just search this whole diagram now. FAC was positive. FAD was negative. FAC was positive. Oops, up here. And FAD was negative. Anything Let's get the others. Did we already get FAB? No. FAB is negative. FBC is positive. And then finally, DE and DC. You get that from node E, which we analyzed earlier. Oh, it's right here. So positive horizontal, negative at the angle. So this guy was positive, and this one was negative. So when we look at this diagram, what this allows us to do is actually recognize how these members will fail under a normal load that's shown here. Now, is this a normal load? 400 newtons, 800 newtons, or is this just a sample problem? It's really just a sample problem. Would a bridge ever have only two forces acting on the top of the bridge? That would be a really weird bridge, wouldn't it? I mean, think about it. Cars, trains, things like that travel over a bridge. So your forces are going to probably be distributed, not concentrated on nodes, and they're most likely going to be on the bottom, not the top. Everybody follow me? Now, we talked about the fact that to do what's called nodal analysis, or this truss analysis, the forces have to be at the nodes, not on the members. So what are we doing? We're simplifying things. If I have 100 cars going across here, maybe I just draw a force down on these 3 nodes instead. Right? 1, 2, 3 instead. Showing that the actual force downward is what's happening. Okay? All right. Let's go on to the next example. So example 1 here says, determine the reaction and the members' forces. So this example is far simpler than the previous one. We just went through all that analysis. So let's start this together and let's think about this. Now, kip simply means kilopound, by the way. It's an old school unit that people have used. It means 1,000 pounds. So really 15,000 pounds is what that's saying. But we'll just use the unit kip. So we'll just leave 15 as it is. So this structure has a simply supported member. And we see that here because this has a pin joint and this has a roller joint. And we talked about this already. A pin means that there is a reaction force here, which we call RAX. And there's a reaction force here, which we call RAY. And then when there's not a pin, but simply a roller on the other side, it means that it's able to move left to right. That's why they're showing like wheels. But there is no way it can move up and down because there's a reaction there preventing motion up and down. So we've got 3 reactions for this member, or this bridge, just like all of our simply supported bridges. Now, because we only have 3 members, this is a lot easier. A lot easier to analyze. So what's the first step from yesterday? What did we do? Yeah, go ahead.
So why did you draw those things?
Because remember, if I were to step on the bridge, why isn't it caving in, Rodrigo? Isn't there support at those locations?
So why about the X one?
The X one is because if I don't have something causing this object not to move left to right, although it might not move up and down, the bridge would just slide back and forth. So we need to prevent lateral motion and vertical motion.
So why is there no one on the other side?
Because we don't need one on the other side. Think about it. If it's prevented one way, can the other side move if it's a structured member? Think about this computer right here. If I'm holding right here in place, holding it, right? And I were to go and push, can it move? If I were to pull, can it move? No. So if I fix it one spot in one location in the X, it cannot slide left or right. Now, you're going to say, well, why do we have them in the X, in the Y where we have 2, right? In the Y direction, though, remember, a pin only prevents motion up and down. So this thing could still rotate, and this pin would not cause this to move. So without having the RBY, this side of the bridge could rotate up and down. But having RBY and RAY prevents it from moving up and down here, prevents it from moving up and down here, and therefore the bridge cannot rotate. It's called simply supported. There's a lot of theory you can read on it, but I'm trying to give you guys like more of an idea of an application of where it will come into play. But these prevent vertical motion and rotation. This guy prevents horizontal motion. If you want to jot that down as why we have them. Now, what do we do though in the first step? What was the analysis method yesterday? We didn't jump right into nodes, remember. Nodes were the second part. So we're not worried about the nodes, the junctures yet. What do we do to start this problem? What did we do to start it? Come on, you did it in your notes. Go back if you have to look yesterday. What did we do to start this problem? Alex?
The sum of the forces x equals 0, and then the sum of the forces of y equals 0.
And then? There was 3 for the starting.
And then you try to solve them.
We tried to, and we couldn't, remember? So we had to use the sum of the moments, remember, or torques?
Yeah.
So the third thing we have to do is the rotational aspect. So let's start with forces, and then we'll get into torques. So if I do sum of the forces to start, let's take a look at what we get. So I've got RAX pushing right. I've got 10 kips pushing right. And I've got nothing else acting, right, in the x direction. So what does that allow me to do? If I have one equation and only one variable, what can I do? I can solve. So because this structure was very simple to start, the first part with RAX is also very simple. Remember yesterday, what was RAX? Or what was the RX value yesterday? What was the RX value yesterday? Or for the last example we just did, I'm referring to. What was it?
0.
Why? Absolutely.
There was nothing, no force being applied to it.
Yeah. Notice we have the 10 kip force here applied left to right. In the last example, didn't we only have vertical forces pushing down? I know they're distracting, Christian. Try not to. I know. I see your eyes just watching them play. Forces are pushing down, right, on the bridge. So the reactions pushing up will respond. But there was no horizontal reaction yesterday because there was no horizontal applied force. Here there is. It's 10 kips. Now, some of the forces in the y direction might seem useful but won't help us. Let's show why that is. I've got RAY pushing up. I've got RBY pushing up. And then I've got 15 kips pushing up. So why can't I solve this equation?
I mean, first of all, you don't know how it's being divided, do you?
Exactly. And how many unknowns are there? There you go.
2.
And how many equations, though?
1.
Only 1. So we can't use simply this equation to get the RY values, A and B both. So what do we go to, like we did yesterday, we said? Sum of the torques. We call them moments. Remember, another word for torque is moment. So you hear that a lot. So we say the sum of the torques, or in this case, we could say the sum of the moments is equal to 0. Now, which location are we going to take the torques about? Remember, torque is about rotating axis. So if I sum the torques about point A or B or C, they're all different values for torque that we're going to get as answers. So will I choose A, B, or C, do you think?
Well, if A is like a pin, it says like a pin, so it's not going to be moving, that's going to be the spot where everything else is going to be turning around it. So
Yeah, but we could choose any pin, any spot, but that is a good idea. Katie's recognizing it's a pin, so that'd be where it'd rotate, let's use that spot. But you could use any of the members. Now, why would node A be smart? Remember, when forces are applied at the node, they exhibit how much torque? None. Remember, torque is F times R. And if this force is acting right here, what's the R value? R is the distance from between the force and the pivot point. Well, the distance is 0, and I gave that example with the door yesterday. I showed how, remember in physics, I opened the door from the handle, it opens easily. But when you try and open a door at the hinge, it pretty much doesn't open because you're not generating any torque. So we're going to take the sum of the torques about point A, or the sum of the moments at A. So RAX and RAY are not involved in this equation at all. They're zeros. Now RBY causes, think about this, RBY would cause counterclockwise rotation, so it's positive, and it's 20 feet away. So I'm going to multiply it by 20 feet. Then take a look at what I'm doing. We did this yesterday. I'm going to extend this force. Please watch. I'm going to extend this force here and make it look like that 10 kips is there. And now I know what is this perpendicular distance here. I can figure it out. I can... Actually, do I know that distance?
Yeah, just on the side.
Oh, thank you. There it is. Thanks, Rodrigo. 10 right there. So I can say that the 10 kip force, this 10 kip force is going to cause this bridge to rotate clockwise. Clockwise is negative, and that's a 10 kip force times a distance of 10 feet. And then finally, the last one is the 15 kips. Extend that one down like this, we said yesterday. And then we can use this distance right here as 10 feet, and it's a 15 kip force, and that's positive 15 kips times 10 feet. The whole thing equals 0. And why is that last one positive? Because this force would cause counterclockwise rotation. This force would cause clockwise rotation. This force would cause counterclockwise. So counterclockwise are positive torques, and clockwise are negative torques. And now we just solve this to get that last reaction. So that's 150, negative over, add 100, that's negative 50, divided by 20, negative 2.5. Can somebody check? Negative 2.5 kips.
I got 50 over 20.
50 over 20. Yep. So what does this mean in this problem? Use logic. Which way is the applied force acting? The 15 kip applied force. It's acting which way? Everybody. Up, right? So which way the reaction is going to have to pull to keep this bridge from moving up? And look at my two answers. Or my answer for RBY is negative 2.5, right? Pulling down. RAX was negative because this was pulling to the right up here, so RAX has to pull back to the left. That's the significance of the negative signs for these two. Now let's get RAY also as our final step, and we can get that from this equation right here. Once we know RBY, we plug that in. Negative 2.5 going in for RBY right here makes that 12.5, which makes this a negative 12.5 kips. Here's what I'd like you to do. You have 2 days, right? I'm going to see you guys tomorrow. I'd like you to try to do the nodal analysis. You can definitely do this for simply the 3 nodes shown. I'll give you a hint. You only have to do 2 nodes. Because once you do 1 node, you'll get 2 of the force members, and then you pick another node to get the 3rd force. So you need to find the force. No, the same problem we're doing. The same one we're doing. I want you to find the force in those 3 members by using the nodal analysis. So look at the 3 nodes to do it. Go back to the example from yesterday if it helps you. Okay, so let's look at nodes A, B, and C and think about which of these makes most sense to identify and isolate. So node A, what forces are acting on node A? And look at your diagram to see the reactions acting and also the members acting. So what do we have? Katie, what are you thinking? And are we talking, Katie, are you referring to the reactions or are you referring to the members right now? Reactions. So we have the reactions that work. So we know that RAY acts upward and RAX acts to the right. Now both of those values turn out to be negative, right? When we solved the diagram earlier. So in reality, they're going to really act down to the left. But I'm just trying to be consistent with my original diagram over here. Everybody see what I'm doing? I'm literally using exactly what was in the bottom left corner. I'm keeping the orientation of the arrows the way they were, and when I plug in numbers, I'm going to plug in a negative sign for both of those. What else is acting at node A? What else is acting at node A? What members are extending from node A? What parts of the bridge? How would you name them based on last class? I can draw arrows to help you. I definitely have an arrow that way and an arrow that way. What would you call them, Katie? Good. Very good. Just literally labeling from one node to the next. So starting at node A in the direction of node C, we call that FAC. Starting at node A in the direction of node B, we call that FAB. So to name the members, you just name the endpoints. Remember in geometry, you were like, why am I learning to name segments, A, B, or BC? It seems boring. Here's one application of seeing that, right? from A to B. That's the segment AB. Well, it's FAB. This name of the subscript is like the segment name that you learned from geometry class. The same thing happens at location B. At location B, I've got the reaction pushing up, RBY. I've also got a force pulling to the left, and I'll call that, again, FBA, though. And I'll say that I have a force acting up and to the left, and that's FBC. And the way I'm naming my forces is from one node to the other. So notice the subscripts switched. Take a look at these two. Notice the subscripts switch. FAB and FBA. FAB and FBA. Just because the order of the subscript switched doesn't mean those are different values. It's still the same beam. It's still from A to B or from B to A. It's the same physical beam. So FAB and FBA are going to be the same values.
So does it matter if it's pointing in two directions, not pointing negative?
No, yeah. So remember how it works with this diagram. The whole concept here is that when we get a positive force as an answer, it means it's intention versus a negative impression. So it's not going to matter. But when we draw our forces from nodes, we always draw them away from the node. So whenever we draw a member force, the arrow is always drawn away. That's automatic. The reactions, we can see here, are drawn how they're shown on the diagram. However they're shown up there is how the reactions are shown. And how the applied forces are shown. So let's look at point C to make more sense of this. Node C has 4 forces acting on it also. Node C has 4 forces. 2 of them are actually given already, so I don't have to actually put letters. I can put values. This is 15, and this is 10. That's already given in the diagram. And my units are kips. That's fine. I'm going to drop it for a minute just so I have numbers because it's all all over the place here. I don't want to get messy. And then I've got 2 other forces. Let me put little lines here to separate these. So at node C, I've also got a force pulling this way, and I've got a force pulling this way. And this is a force extending from node C to node A. That's a force extending from node C to node B. So those are my 3 nodal diagrams. And clearly those are my 3 free body diagrams. Like from physics class, we're using free body diagrams again to give us an idea of how the forces are oriented or how they're applied to the member. Now that member happens to be the node, right? The pin. The pin that's going through that junction at B or at A or at C. Now look at my 3 free body diagrams. Look at all 3, please. Tell me, which of them might you start to solve? Which of them might you start solving first? Why C? Okay, so in C we've got 2 unknowns, right? How many unknowns do we have here? Be careful, kid. You're saying 3, but I think we have RBY right, don't we? So this is still 2 unknowns, and this is still 2 unknowns. So they're all 2 unknowns, right? All 3 diagrams, I'm missing these 2, I'm missing these 2, I'm missing those 2. I'm never missing the reactions because I have the numbers, which maybe I'll put them in there to make it clear. So I'm only missing 2 variables in all 3 scenarios, so that doesn't limit my choice. What are you thinking?
But if you choose C, don't you get FCA and FCB, so then you just have to find one on A and one on B?
So the issue with choosing C is that this has a horizontal and a vertical component, right? Part of this pulls left, part of this pulls down. This one also has part pulling right, part pulling down. So you'll end up with 2 equations and 2 unknowns, which is okay, but you'll have to solve a system if you use the free body diagram at node C right now. There would be a system in place. Whereas here, because this is only horizontal, or because this is only horizontal, you would be able to solve for FBA once you get FBC, because FBC is both in the X and in the Y. So we can get FBC by only looking at the Y direction, or we can get FAC by only looking in the Y direction for these 2 diagrams. So because these are both at angles, we don't want to really start with that one. So let's write a note down. Let's write a note down. If our 2 unknowns are both at angles, we have to solve a system of equations. We don't want to do that really. Life is easier when we don't have to do that extra math. So I would start this option or this analysis at either node A or node B. And I'll show you what I'm referring to. Let me show you with node A. It'll make more sense if I write out the equations themselves. I'm first also going to plug in my values for R's. I'm going to write them in. So RAX is negative 10. RAY is negative 12.5. And RBY is negative 2.5. So I'm labeling them on my diagram so I don't forget. Okay, so I just labeled all the reactions with their negative values. They're all negatives, we know that already. Now, if I look at node A and only node A, if I look at node A alone, I'll notice that FAB, I'll point to it, FAB right here, and FAC both act to the right. Does everybody agree with me that these two forces both pull to the right? So they would both appear in the equation for X. If I did sum of the forces in the X direction, these would both appear, and we would not be able to solve for either of them. But if I do sum of the forces in the Y direction, does FAB play a role in the Y direction at all? Does FAB play a role at all in the Y direction? No. It's only pulling horizontally. So if I look at the sum of the forces in the Y direction to start, that makes life a lot easier. I've got the following here. I've got RAY pushing up, and I've got FAC pushing up. That's it. Now FAC, I have to multiply by the sine of the angle. Now, do we have an angle in this diagram? Take a look at the diagram. I'm going to need some sort of an angle, right? Take a look at where I'm looking first. Again, I'm at node A. I'm trying to find out this angle right here. Look at where I'm labeling theta. I'm in node A. I'm trying to find out that angle so I can do FAC times the sine of that angle, which is what's missing in that equation still. And I'm still missing times the sine of that angle. So the question is, what is that angle? Well, let's look at the diagram. That's the angle between FAC and FAB, which is this angle right here. Right? That's that angle that we're referring to right there on the diagram. So we have to figure out what that angle is. Can we do so? Can we figure it out? Let's call these angles values. This is theta that I just labeled right here. That's the same theta we're talking about right there. Can I figure it out? How can I figure it out if so? Come on, figure it out. Figure it out, figure it out, figure it out. It's geometry. It's in there, it's hidden.
Well, you have to do like
You think you would at first. You can do all that work. Absolutely, Katie, you can. But there's an easier way for this one. It's an easier way. But you're right. You can use SOHCAHTOA. Okay.
So if you do the inverse of like,
Keep in mind that that only is true for right triangles. Do we know if this is a right triangle yet? We don't know yet. Chris, what are you thinking?
We can make the right triangle by cutting the bottom in half and move the bottom length and the height too.
What's this length right here, Chris?
That's 10.
And what's this length right here?
That's 10.
10 root 2. Remember, this is a 45, 45, 90? Whenever these are both 10s and this is a right angle, this has to be a 45, 45, 90. You remember your 45, 45, 90 triangle? It's an isosceles right triangle. So Chris makes a really good point. So we can go into trigonometry. And Chris said, hey, that's a 10, that's a 10. I can do the tangent of theta equals 10 over 10. But when does the tangent of theta equal 10 over 10? When the angle theta is 45, or the tangent ratio is 1. So what Chris is pointing out is, if we don't see the triangle, we could extract it. I'm going to draw it at the top. 10, 10, and theta. Okay, so Chris is literally saying, hey, let's pull this triangle out of the triangle. We'll cut right down the middle there and recognize that this is 10 by 10 by x. We don't care about the hypotenuse. We care about the angle. So if we're confused, we can say the following. Right, we can say that. The tangent of theta equals opposite over adjacent, which is 10 over 10. So theta is the tangent inverse of 1. Because 10 over 10 is just 1, right? And the tangent inverse of 1 is always going to give us 45. 45 degrees. Okay, so again, if you didn't remember that this was a 45, 45, 90 because it's 10, 10, and then something missing, then you could use your trig ratio and you'll get 45 degrees as an answer. But the key to remember here is that, yeah, hey, it's a 45, 45, 90. 30, 60, 90 and 45, 45, 90 show up so much in structural components, it's incredible. And you wonder again, right, from your Algebra 2 trig last year, why did you memorize S, 2S, S root 3, remember that, the 30, 60, 90? Or S, S root 2? Those reasons are because they just show up so frequently. You get 30, 60, 90s all the time. When you have an equilateral triangle, if you have an equilateral cut down the middle, you end up with two 30, 60, 90s. That's what you get as a result. Okay, and the other case here is the 45, 45, 90. So that angle is 45 degrees, which means that when I analyze node A all the way back over here, that same angle theta is 45 degrees. So since that's 45 degrees, I know it's the sine of 45 there, and that whole thing is going to equal 0. Again, because the sum of the forces in the y direction only includes two forces. There is no component of FAB, because FAB only acts horizontally. Again, look at the diagram. FAB only acts horizontally. So it doesn't go into play for the sum of the forces in the y, and that makes life easier. Because now I can plug in for RAY, that's negative 12.5. Right, that's right here, it goes in for RAY. Plus FAC, sine 45 is root 2 over 2, or 0.7071, or just leave it as sine 45. And then solve for FAC. Move the 12.5 over. And then divide by sine 45. Okay, that'll give us FAC. So the key to this process is I specifically chose the y direction and not the x direction, because the x direction had two unknowns. Both FAC and FAB were unknown in the x direction, but only FAC was unknown in the y direction. Okay, question?
No, just add the answer.
What do you got?
17.67.
17.67 sounds about right. It's got to be more than 12.5 because I know I'm dividing by the sine of an angle, which is always less than or equal to 1. Right, this is going to be some decimal, which is 0.7071. So my answer's got to go up. So that sounds reasonable. Now, that gives us FAC, but from node A, we can also get FAB. Without even going on to the next two nodes, right, without going to node B or node C, let's continue with node A. Now that we know FAC, we can look at the sum of the forces in the x direction. In the x direction, let's look at the sum of the forces now. Okay, good. You sure? You can ask. Sum of the forces in the x direction. Somebody want to step me through the formula that I would get from this? Yeah?
So, should you want me to do the letters? Or
Yeah, the letters, the original that we have.
We're doing the sum of RAX
Good.
plus FAC plus FAB.
What's missing next to the
Sine.
x
Oh, cos
equals?
theta. 0.
Good. So there's my formula for the x direction. It looks very much like the y direction, except we've got this extra additional force of FAB. So look, this is what I meant. 1, 2 unknowns. So if I started with the x direction, this is not solvable. That's why I started with the y direction to get FAC, Let's plug that in here for FAC now. So again, I can now analyze the x direction because I can plug this in for FAC, and RAX is all the way from over here. And this is going to be a long arrow I'm going to draw. Here's RAX coming all the way around from over there. So I've got RAX, I've got FAC from the y direction, which allows me to solve for FAB. So RAX, again, is going to be negative 10 plus 17.67 cosine 45 plus FAB equals 0. So once I get one of my members, it allows me to solve for the other members much easier. So getting FAC was very useful there because now we're using it to get FAB. So let's add the 10 over and subtract the 17.67 cos 45. Again, I'm going to add 10 over and subtract the entire 17.67 cos 45. What do I get as a number? Can we move on? Katie, what do you got? Let's see. Yeah, it sounds reasonable because this is going to be about 3/4 of this number, which is around 12.5. 10 minus 12.5, around negative 2.5. So all the negative sign means is what again? What does the negative sign indicate again for these problems? What is it? Yeah, but more specifically for the members. For the members, a negative means compression. Tension, think positive, the letter T, positive. So this member is in tension, this member is in compression. Now, how many members do we have left at this point? How many members do we have left? Just one. Believe it or not, just one. It looks like maybe two because we have two nodes left. We have two nodes left to analyze, right? But take a look. We've got FAC right here. So please plug it in for FAC right here. We've got it. We got FAB right here. Let's plug it in for FAB right there. That leaves FCB or FBC, which is the same thing actually. Looking like two unknowns, but we really only have one unknown left. So again, FAC is 17.67. Let's write that in. And FAB is negative 2.49. So if you're not sure what I just did, take a look where I'm circling. I crossed off FBA and wrote in the value of the force of negative 2.49. I crossed off FCA and wrote in the value of the force, which is 17.67. Now, it allows me to look at the node C or node B setup to solve. Does it matter which one I choose now? There's only one unknown left in either scenario. Whether you look at node B or node C, there's still only one unknown left over. So you can pick and choose whichever one you like here. Okay, it doesn't make a difference either way we go, whether it's node B or C. I will choose, I don't know. Let's choose node B. I'm just going to do it just because node B is the first one that appears. Now, with node B, I'm going to start by looking at the sum of the forces. I could look at the sum of the forces in the y or the sum of the forces in the x. Does it matter which one I choose? I want you to honestly think. Does it matter? Look at node B. If I look at sum of the forces in the x, I've got FBC acting in the x, and I've got this acting in the x. If I look at sum of the forces in the y, I've got FBC acting in the y, and I've got this force acting in the y. So in both cases, I've got a component of FBC and another known, or a component of FBC and another known. So is it any different whether I do x or y direction for force here? There's no difference whatsoever. So it doesn't make any impact on your problem. I'm going to start with some of the force in the y direction. Again, it doesn't matter either way. In the y direction, again, I've got FBC pulling up times the sine of theta, because it's the y direction, plus ray equals 0. I'm sorry, RBY. I put A, RBY. Right, we're on node B here. RBY. So RBY is drawn upward in the diagram, that's why I put the positive. But we got an answer for RBY earlier, which was negative 2.5 kips. So RBY will go in as a negative 2.5. After that, I've got FBC that I'm looking for still. What's the angle theta in this problem? What's the angle? Yeah, it's the same angle, right? Take a look. This is our angle theta right here. It's the same angle as this angle theta was up here because this triangle exhibits. What does it exhibit? What's the word in math? And flip it over a line, it exhibits reflection, but what's the general word? Symmetry. It exhibits symmetry here. So because it exhibits symmetry, the angle of theta must be 45 here. So this is sine of 45. And then it becomes just solving for FBC. Oops. And it becomes solving for FBC. So if I wanted to get FBC by itself, I would add over the 2.5 and then divide by the sine of 45. And again, I would add over the 2.5 because it's currently negative, add it over, and then divide by sine 45 to get FBC. But I know it's going to be more than 2.5 because I'm dividing by a decimal again. So this last member, because it's a positive answer, must be in tension. So we've got the reactions at A, both. The one reaction at B. We've got the forces acting in members AB, BC, and AC. And that's that way we analyze or structurally analyze the forces acting on a bridge, or on a truss structure in general. Questions on this? This is the second example we've done only, right? It's only the second example. So tonight I'm going to have you guys do a couple examples to practice. Probably have you do 2 examples. Well, not tonight. I don't think I see you guys tomorrow, right? It's day 6. So I see you guys on day 2 again, right? So you have 2 nights technically. You have tonight, a couple nights. 2 nights. 6, 1, 3 nights actually. Yeah. You have a couple nights. I'm going to give you 2 examples to practice. I want you to take the exact same approach we took here. You start with the bridge as an overall structure, and then you then move on to the 3 nodes, or however many nodes there are, analyze those nodes, and then do the sum of the forces. I think that the hardest part students find for this is honestly recognizing when to realize what the angles are, if there's symmetry, the geometry involved. So that part can get a little bit tricky. But after that, the routine is the same. It's always sum of the force in the x, sum of the force in the y. It's always sum of the moments or torques when you're doing the bridge. So it's not going to change in process ever. Okay? It's not going to change in process. All right, let's stop.